Have you ever been in a car, crossing a massive bridge that spans a wide river or a deep valley? You look out the window and you see hundreds of other cars, trucks, and maybe even a train, all moving together on this giant structure suspended high in the air. It's a question that gets more amazing the more you think about it. Every single day, bridges around the world carry an incredible burden. They face constant pressure from traffic, wind, and even changes in temperature. At its core, every bridge is in a constant, invisible battle with one of the most powerful forces in the universe, gravity. Gravity is relentlessly pulling every single part of the bridge and everything on it straight down. So the hidden problem that every bridge engineer must solve is not just how to build a flat road over a gap, but how to defeat gravity. They need to design a structure that can take all that downward pulling force and redirect it safely into the ground. To understand how they do it, we need to meet the two main characters in the story of any bridge. Their names are compression and tension. Compression is a squeezing or pushing force. Imagine you are pressing the palms of your hands together as hard as you can. You can feel the force pushing inward. That is compression. Tension is the opposite. It is a stretching or pulling force. Think about pulling on a rubber band from both ends. The force you feel trying to stretch it is tension. Every part of a bridge, at every moment, is experiencing one or both of these forces. The genius of bridge design is in arranging materials in a way that uses these forces to create strength instead of weakness. The story of how we learn to manage these forces is the story of how bridges evolved. It starts with the simplest design imaginable. Think of a log or a simple plank of wood laid across a small stream. This is a beam bridge. It's the most basic type, and it shows us the fundamental challenge. When you step on the middle of that plank, it bends. The top surface of the plank gets squeezed together, experiencing compression. At the same time, the bottom surface gets stretched apart, experiencing tension. If the weight is too heavy or the plank is too long, the tension on the bottom becomes too great and the plank snaps in half. This is the limitation of a simple beam bridge. It can't span very far without extra support. An arch bridge is a brilliant solution to the compression problem. The curved shape of the arch takes the downward force of gravity from the top and, instead of letting it bend the bridge, it channels that force outwards and downwards along the curve. Think of an old stone archway. Each stone, called a voussoir, is wedge-shaped. When weight presses down on the arch, the stones can't move down because they are supported by the stones next to them. They just push against each other more tightly. This is pure compression. The force is guided all the way down the arch and into the ground supports, called abutments. The abutments are massive, heavy structures on either side of the gap that push back, keeping the ends of the arch from spreading apart. The Romans were masters of the arch, and some of their bridges and aqueducts are still standing after 2,000 years. But arches can be expensive to build and aren't always practical for every location. So engineers found inspiration in another simple shape, one that perfectly balances both tension and compression. That shape is the triangle. Triangles are naturally rigid and incredibly strong. Unlike a square, which can be easily squished into a diamond shape, a triangle holds its form under pressure. This led to the invention of the truss bridge. A truss is a structure made by connecting many triangles together into a frame. You've probably seen these bridges with their distinctive crisscrossing patterns of steel beams. When weight is placed on a truss bridge, some of the beams are put under compression and others are put under tension. The network of triangles spreads the load out across the entire structure. No single point has to bear too much weight. Each triangle supports its neighbors, sharing the forces of tension and compression until they are finally transferred down into the supports on either side. It's an incredibly efficient way to build a strong, rigid, and relatively lightweight bridge that can span longer distances than a simple beam. Beam bridges, arch bridges, and truss bridges solved many problems. But to cross the widest rivers and deepest bays, we needed to take a giant leap. Think of the Golden Gate Bridge in San Francisco, or the Brooklyn Bridge in New York. These are marvels of engineering that seem to defy gravity itself. A suspension bridge works by completely flipping the problem on its head. Instead of pushing the load down into the ground with compression, it hangs the load from above using tension. The main components are two gigantic towers, two massive main cables that are draped over them, and hundreds of smaller vertical cables called suspenders. The roadway, or deck, doesn't support its own weight. Instead, it is held up by the suspender cables. All the weight of the cars and the deck itself is transferred as a pulling force, or tension, into these vertical cables. These suspenders then pull down on the two enormous main cables. These main cables are the true workhorses of the bridge. They are bundles of thousands of individual steel wires, creating a rope of almost unimaginable strength. The entire weight of the middle of the bridge is now hanging in tension from these two main cables. So where does all that force go? The cables are draped over the tops of the two colossal towers. The towers take all that downward pull from the cables and convert it into a massive compression force. The towers are built to be incredibly strong under compression, and they funnel all that weight directly down into their foundations, which are sunk deep into the earth or bedrock. But that's not the end of the story. The main cables don't just stop at the towers. They continue on to the land on either side, where they are anchored into enormous blocks of concrete. These anchorages are the final destination for the force. They are buried deep in the ground and are heavy enough to resist the immense pulling force or tension of the main cables. So let's trace the path of the force one more time. The weight of a car pulls on the deck. The deck is held by the suspenders in tension. The suspenders pull on the main cables, also in tension. The main cables are held up by the towers in compression and pulled tight by the anchorages in tension. Another variation on this idea is the cable-stayed bridge. Instead of two main cables, these bridges have many smaller cables that stretch directly from the towers down to the roadway. Use tension in the cables and compression in the towers to hold everything up. Engineers also have to account for other forces. Wind can cause a bridge to sway, so the shape of the deck is often designed aerodynamically, like an airplane wing, to let the wind flow smoothly around it. Heat and cold can cause the materials of the bridge to expand and contract. To handle this, engineers build special expansion joints into the roadway, which allow the bridge to get slightly longer or shorter without breaking. So, from the simplest plank of wood to the most complex suspension bridge, the secret isn't one single trick. It's a deep understanding of these two fundamental forces. Every bridge you see is a different solution to the exact same puzzle. How do you get a force from the middle of a gap safely to the ground on either side? Do you push it down and outward with an arch? Do you spread it out with a network of triangles in a truss? Or do you hang it from above with massive cables? The great insight here is that the most complex and awe-inspiring structures we build are governed by the simplest of principles. It's not magic holding these bridges up. It is the clever manipulation of push and pull, squeeze and stretch. It is the art of turning a force that wants to destroy into a force that creates stability. Engineers use these principles, combined with incredibly strong materials like steel and reinforced concrete, to build structures that are both elegant and immensely powerful. They are playing a high-stakes game of chess with gravity, and their pieces are tension and compression. Every beam, every cable, and every bolt is a strategic move. So the next time you cross a bridge, take a moment to look at its shape. Is it an arch? A truss? A suspension bridge? Try to see the invisible forces at play. See the compression in the towers and the tension in the cables. See the genius of the design that is quietly and constantly winning its battle against gravity. You are not just traveling over a river. You are moving through a masterpiece of engineering, a monument to the simple, powerful idea that by understanding our world, we can achieve the impossible.